Hi there, I am RYC. I am going to be giving a talk today called Gamma and Pi. I gave this talk on Pi Day to the Mathematics Discord. This is a recording. So let's get started. So what are we talking about today? Gamma and Pi. Okay. So I'm going to start the talk by talking about the factorial and what the gamma function is. And then we're going to see how the gamma function relates to pi. And then near the end of the talk, we're going to do a more complicated relationship where we prove something called Stirling's formula, which is a really, really important approximation for the factorial for large numbers. Okay, so let's start by going back to the basics. What is the factorial? Well, suppose you have n objects, and you want to arrange them. So say we have 5 objects, and we have 5 spots. And we want to know all the ways that we can put those objects into those spots, okay? All the different orders. Well, in the first spot, we have 5 different options, right? Once we've used up one, now we have 4 different options for the second spot. Once we've used up 2, we have 3 options for the third spot, and so on. At the end, we're only left with 1 possible object left. Okay? And if we multiply all these to get the number of possible ways of ordering, we're going to get, in this case, 120. And we call that number 5 factorial. So the factorial is going to give us the product of all the numbers from n down to 1. Okay? So this is how we define the factorial. And we can use the factorial for all kinds of things. It comes up in combinatorics, it comes up in probability, it comes up in calculus when you study Taylor series. So it really is an important thing. The factorial satisfies a really important property, which is called its inductive property. Okay. So what does that say? That says that if you want to find the factorial of n, you can find it by first finding the factorial of n minus 1, and then multiplying that by n. And that makes sense, right? Because if we look at our formula right here, this is just the factorial of n minus 1. And then in order to get the factorial of n, we just needed to multiply that by n. So this is one way of understanding the factorial through this formula. Okay? As long as we know what the factorial does at 0 or at 1, then what we can do is we can use this formula to go from 1 to 2, from 2 to 3, and so on and so forth. This is called induction. Okay? So for example, using this formula, let's try to understand what the factorial of 0 should be. Well, if we pick n equals 1, then we get that 1 factorial is equal to 1 times 1 minus 1 factorial, which is 0 factorial. Okay? Well, we know that 1 factorial is just 1. And so if we divide 1 by 1, we get that 0 factorial should be equal to 1. So that's kind of interesting. You might think, shouldn't 0 factorial be equal to 0? Well, no. In the end, actually, it's fine to have 0 factorial equal to 1. This will end up making sense. You can think of this as sort of the empty product. So if we have an empty sum, if we don't sum any numbers, then we get 0. If you have an empty product, you don't multiply any numbers, you get 1, because 1 is the multiplicative identity. Okay? So this is kind of to be expected. Okay, so with that in mind, we can try to calculate the factorial of minus 1. So how do we do that? Minus 1 factorial. Well, let's use our formula. We know that minus 1 factorial times 0 should be equal to 0 factorial. So this guy times 0 should be equal to 0 factorial. We know that that's 1. But now we've got a problem. We have 0 over here and we have 1 over here. So we want to say that minus 1 factorial is equal to 1 over 0, but that's undefined. So actually, minus 1 factorial is not well defined. Okay? And so it might look to you like it should be infinity or minus infinity or something like that, and it's going to turn out that that's kind of what actually happens. Okay. All right, so we've extended the factorial function to 0, but how do we take factorials of other numbers besides the integers? Okay. So it turns out that there's a really special tool for doing this in math that comes up in number theory and analysis and other places in math called the gamma function. And I'm going to write down the gamma function for you, and then we'll talk about why this is related to the factorial and why it extends it. So the gamma function is going to be defined in terms of an integral. So s is our variable here. Okay, so we're going to plug in a number for s. And we're going to take an integral from 0 to infinity of t to the s minus 1, e to the minus t, dt. So here, t is the variable of integration. So s is going to be a constant. So then this thing is going to end up being like a polynomial, and we're multiplying it by e to the minus t. Okay? And then we have to integrate that from 0 to infinity, and we're going to get a number out of this. All right? So this gives you a number for every possible input s. Okay? Well, at least if s is greater than 0. If s is equal to 0, then we get something, we get t to the minus 1 times e to the minus t, and we're not sure if we can integrate that. It turns out that we can't, because 1 over t does not have a finite integral from 0 to 1, or 0 to infinity. Okay? So this is going to be the range on which we can define the gamma function. All right. And now let's look at some facts about the gamma function. So let's try to understand, first of all, what properties it satisfies, and then we'll see why those properties tell us that it's related to the factorial. Because it seems like I kind of just wrote this down out of nowhere, but it actually comes from somewhere important. Okay. So first of all, let's look at gamma of 1. All right. So gamma of 1 is just equal to the integral from 0 to infinity of t to the 1 minus 1, e to the minus t, dt. Okay, but 1 minus 1 is 0, so this is the integral from 0 to infinity of e to the minus t, because t to the 0 is just 1. And then that guy right there, well, we can integrate minus e to the minus t, evaluated from 0 to infinity. At infinity, this is just 0, and at 0, this is just minus 1. So we get 1 for our answer. And so we find that gamma of 1 equals 1. Okay. Now we could go ahead and compute gamma of 2 and gamma of 3 and so on, but what we should do instead is take a lesson from the factorial function, which is that we understood how to compute the factorial of larger numbers by looking one number down and then finding a formula in terms of that. Okay. So let's try to understand what's the value of gamma at s plus 1. All right. Let's see if we can find a formula for that in terms of gamma at s. Well, let's write this down. This is the integral from 0 to infinity of t to the s plus 1 minus 1 e to the minus t dt. Okay. Well, the integral from 0 to infinity of t to the s, e to the minus t dt, as long as s is greater than 0, or is greater than 1, I think greater than 0 is fine, yeah. As long as this is greater than 0, we can do this by integrating by parts. So what I'm going to do is I'm going to try to convert it to a situation where we have t to the s minus 1, so that we have gamma of s. And if I want to do that, then I can integrate I can differentiate the t to the s part to get t to the s minus 1, and I can integrate the e to the minus t part. So how do I integrate by parts? This gets differentiated. This gets integrated. And when I do that, well, first of all, I have the boundary term. So that's when I leave this guy and I integrate this guy. So t to the s minus e to the minus t. And that gets evaluated on the boundary. Okay. And then also I have the integral term. So that comes from differentiating this guy. So s t to the s minus 1. Remember that s is just a constant. It's just the number that we plug into the gamma function. Okay. And then this guy is minus e to the minus t dt. All right. And now I can pull out the minus, and I can pull out the s. And I just get, and I should say, this guy at 0, 0 to the s is 0, so that's going to be fine. This is why we need s to be equal to, or to be greater than 0. Okay. So 0 to the s is 0. And then at infinity, the limit as this goes to infinity is going to be 0, because e to the minus t goes to 0 really quickly, and t to the s goes to infinity slowly compared to e to the minus t. Okay. So this guy is just 0 minus 0, and that's going to be fine. And then over here, the minus sign cancels out and the s pulls out, so we get s, the integral from 0 to infinity, t to the s minus 1, e to the minus t, dt. But this guy was just equal to gamma of s. Okay, so what did we find? We found that gamma at s plus 1 is equal to s gamma of s. This is sort of similar to the formula for the factorial that we found earlier. It's a little bit different, but it shows us that we can find the value of the gamma function at s plus 1 in terms of the value of the gamma function at s. Okay? It satisfies an inductive relation. Okay. Now, using this, let's try to understand what the value of gamma at the integers are, right? Because we already understand what gamma of 1 is. And now we can use this to get gamma of 2, and then gamma of 3, and so on and so forth. Okay, so if we try this for a few numbers, we'll see that gamma of 2 is equal to 1 times gamma 1, which is equal to 1. Gamma of 3 is equal to 2 times gamma of 2, which is equal to 2 times 1. Gamma of 4 is equal to 3 times gamma of 3, which is 3 times 2 times 1, which is 6. And we see a pattern starting to develop. Okay. We see that the gamma function is actually giving us the factorials. Well, it's giving us the factorials of the previous number. Okay. So for example, gamma of 4 gave us 3 factorial. So let's try to prove this. So let's try to prove that gamma of n is actually equal to n minus 1 factorial, as long as n is greater than or equal to 1. How do we prove something like that? We use induction. So how do we do induction? Well, we'll start with the base case, n equals 1. In that case, we already showed that gamma of 1 is just equal to 1, but we also showed that that's equal to 1 minus 1 factorial, because that's 0 factorial. Okay? So we verified the claim in the base case, and now we need to do the inductive step. So what does inductive step mean? It means we assume that it held at level n, and then we prove that it holds at level n plus 1. And as long as we do that, we can go from n equals 1 to n equals 2, 2 to 3, 3 to 4, and so on and so forth. Okay. So let's do this. The inductive step here is assume gamma of n equals n minus 1 factorial for some n. Then we need to show it for n plus 1. Okay. So then the only thing that we can do is we can look at gamma at n plus 1. But we know from our formula that this is just equal to n gamma n, because we proved that gamma s plus 1 is equal to s gamma s for any real number s greater than 0. Then we can use that we know that gamma n is equal to n minus 1, so this is n times n minus 1 factorial. And now we can use the equation for the gamma, or for the factorial, which said that n times n minus 1 factorial is just equal to n factorial. Okay? And so with that, we proved the fact that we wanted to show for n plus 1. which means that we've proven it for all n by induction. Okay, so that says gamma n is equal to n minus 1 factorial for all n. Okay. Great. So we found a function that actually tells us what the factorial is for integer numbers, well, as long as you shift. But it also lets us extend the factorial to other real numbers besides the integers. Okay. So this is pretty interesting. It's a useful thing we could use. Now you might wonder, okay, if we drew a graph and we just filled out at the integer points the factorials, so like here, 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 and here. Okay, here is factorial of 0 and factorial of 1, factorial of 2 goes up like this, factorial of 3 goes up like this, and factorial of 4 goes way up. And so we could draw, some sort of graph through these points. But we could draw tons and tons of graphs through these points. I could draw anything that I want. So what's to say that the gamma function that we came up with is the right way to extend the factorial to the real numbers? And I can draw what the gamma function looks like. It looks something like this. It's a very, very smooth extension to the real numbers. Okay, it's a very nice smooth. It doesn't bump. And so that actually comes from something called log convexity. So let me say what that means. Okay, so I'm going to introduce a theorem that we're not going to prove, but it's an interesting theorem that you can go check out if you like, called the Bohr-Mellerup theorem. Okay, and what does this theorem say? It says that of all the possible ways that you could extend the factorial function, there's only one way. There's only one way that is actually really good. Okay? And that's the gamma function. So it says that gamma is the only function, it's the only positive function f on the positive reals. Okay? Such that the following are satisfied. F of 1 equals 1. We have the equation that we want, f of x plus 1 equals x f of x. So remember that we used these two to show that gamma of n was equal to n minus 1 factorial. Okay. And finally, we have one last relation that our function needs to satisfy in order to be the factorial, in order to be the gamma function, which is that log of f of x is convex. This is sort of a weird statement, okay? So as long as we require that log of f of x is convex, then if we satisfy these two properties, you end up having to be the gamma function, which is kind of surprising. It feels like there should be a lot more leeway here, because we could wiggle in all kinds of ways through our points. Okay? What is log convexity? Well, if I take a function and I take its log, then I could ask questions about that new function that I get. In particular, I could ask questions about whether or not it's convex or concave. So let me remind you what a convex function is. If you have a function, then this function is not convex because it doesn't look like a bowl, right? So a convex function is a function whose second derivative is going to be positive everywhere. But in this function, right here, the second derivative is negative. Okay. So in general, a convex function is going to look more like this. So being a convex is a pretty heavy requirement on a function. They don't all have to be parabolas, but they will look something like a parabola. They'll look like a bowl. Okay. So why would we ever want log of a function to be convex? Well, it turns out that this is a really useful property in a couple different fields of math, including analysis and other areas of math. being log convex is very restrictive, and it gives you good properties about how the function acts, for example, on the complex numbers. So one thing that we'll talk about in a bit is how the gamma function is the analytic continuation of the factorial function to C. Okay? So this is one way of understanding the gamma function. So you don't have to think too hard about log convexity for now, but it turns out that even this very simple seeming property, that this log of f of x has positive second derivative, is enough to tell us the gamma function uniquely. It's the only function that satisfies this. If you want to see the proof of the Bohr-Miller theorem, you can look it up. It's not too complicated of a proof. It's just kind of messy, but you should be able to read it with what you know, assuming that you know some basic analysis and calculus. Okay. Cool. Okay, so I've defended for you why the gamma function is the right function to choose after I just wrote down some crazy integral and said, let's work with this. First of all, we saw that it extends to factorial, and second of all, we saw the Bohr-Miller theorem, which says that it's actually the unique good function to extend the factorial. All right. So now that we have this function, let's try to compute gamma at some interesting values, so that we can understand how the factorial should extend to the real numbers. For example, we can try computing gamma at 1/2. Now, this isn't exactly factorial of 1/2. Remember that gamma of s is equal to factorial s minus 1. So this is something like 1/2 minus 1 factorial, or minus 1/2 factorial, which is also pretty cool. But after this, we can use our equation for the gamma function to then compute the gamma function at fractional integers, or at half integers at least. Okay, so we can use this to compute gamma, or factorial of 1/2, and then up from there. Okay, so how do we compute this? All right, and my claim for you, I'm going to spoil it right away, that this is actually going to be equal to the square root of pi. Where did that come from? Isn't that weird? Why does it have a square root of pi in it? This is a very, very strange fact, and we'll see why it happens. Okay. So if you're familiar with something called the Gaussian integral, this is related to that. Okay, so how do we prove this claim? So let's just write down what we have. That gamma of 1/2 is equal to the integral from 0 to infinity of t to the 1/2 minus 1 e to the minus t dt. Okay, and then if we simplify this, we can write this as t to the minus 1/2, which I can just write as 1 over the square root of t. Okay, and this integral does not look very nice. If you spent some time doing Calc 2, then you'll probably know right away that this function does not have an elementary antiderivative, or maybe you won't know that right away, but you wouldn't be surprised to hear that. It's a pretty nasty function, but we can at least try to get somewhere with it, okay? Because we're not computing the indefinite integral, we're just computing a definite integral, and so maybe there's some hope of figuring out what it is. So the first thing that I'm going to do is I'm going to do a u substitution. Okay, so let's try t equals u squared so that we can get rid of the square root. If we do that, then we get that dt is equal to 2u du. But u is equal to square root of t, so this is equal to 2 square root of t du. Okay. And now we are going to replace this. So when I plug in 0 and infinity, I just get the same thing. When I plug in dt equals 2u du, I get 2 square root of t du. So 1 over square root of t e to the minus, and then here I'm going to use the fact that this is u squared, and then I'm going to write 2 square root of t du, and then of course these guys are going to cancel out. Okay, so with that I get that this is equal to 2 times the integral from 0 to infinity of e to the minus u squared du. Okay, so we've come up upon something called the Gaussian integral. This is a really, really, really important function, e to the minus x squared. Okay, this function comes up in statistics, it comes up in analysis, it comes up in probability theory, all kinds of places. It's such an important function But it doesn't have an elementary antiderivative. You can't write down the antiderivative of this function in terms of the usual functions that you want to use. In fact, it's so important that the antiderivative has its own special name called the error function, or ERF, that you might have seen in statistics. But it turns out that we can compute the integral from 0 to infinity of this function. Or what I'm going to do is actually compute the integral from minus infinity to infinity, because this is an even function. If you plug in minus x, then you just get the same thing. And so the integral from 0 to infinity is the same as the integral from minus infinity to infinity. And so then I'm just going to use this 2 here to say that this is going to reflect over and give us the full interval. So how do I do that? I'm going to erase the 2 and just replace from minus infinity to infinity. Okay. So the Gaussian integral can be done in a few ways. Some of you have maybe never seen this before. Some of you might have seen it and have seen a very particular way of doing it using polar coordinates. Today I'm going to do it a little bit differently. Okay. So I'm going to use the cross-sections method that we learn in Calc 2 to compute the volume of objects. Okay. So first of all, I'm going to need to write down something that I can compute with. So first of all, I'm going to square. Well, why do I want to square? Well, I claimed for you that the answer would be equal to the square root of pi. So maybe if I square the integral, then I'll have some hope of getting to pi, because that seems a little bit more natural. And then when I take the square root, I'll get square root of pi. Okay. And if I square this integral, it doesn't look so good as is, but I can write it as the integral multiplied by itself. Okay, and then I'm just going to change the variables because I don't want both of these to be u, so I'm going to change this variable to x. I'm going to change this variable to y. This doesn't matter, of course. In the end, I'm just going to get a constant number anyway. Whatever the variables are is not going to make a difference. And then I'm going to do something kind of tricky. So I'm going to think of this guy as a constant c. Okay. Because in the end, after you do the integral, it doesn't have any variables in it. It's just a constant number. And then I know that I can push constants under integrals. So I'm going to say that this is equal to the integral from minus to infinity of e to the minus x squared dx times c on the inside. All right, so now let's write in what c was. Okay, and now at each point of this integral, we have a particular value of x, right? So you just think about this. At each point of this integral, we have a particular value of x that we're using. We plug it into e to the minus x squared. And then that just becomes a constant. So I can actually now treat this as a constant, and I can put it into this integral. Now, this part might be a little more iffy if you haven't seen this done before, but trust me, it works. This comes from something that I'm doing called Fubini's theorem, okay, from multivariable calculus. So I'm going to take that e to the minus x squared, which doesn't depend on y, so it's a constant with respect to y, and I'm going to put it into the y integral. Okay, and now we have something that looks suspiciously like a multivariable integral. So if you haven't done Calc 3, that's okay. This is the only part in which we're going to use a tiny bit of Calc 3, and I'm going to say what exactly we're doing, so don't worry about it. Well, the first thing that I'm going to do is I'm going to use the property of the exponent to say that this is just e to the minus x squared minus y squared, or e to the minus x squared plus y squared. Okay? And then I'm going to write this as the integral minus infinity to infinity dy, integral minus infinity to infinity dx. Okay, and then what is that quantity? So if you know a little bit of multivariable calculus, or even if you don't, you might guess that this is going to be the volume underneath this function. So if I let this, that be called f of xy, so if I define a function by that, then I can draw the graph of this function on the x, y, z space. Okay, so this is the x direction, or wait, this is the x direction, this is the y direction, this is z. And what am I going to get? I'm going to get a function that looks kind of like a bump. Like this. All right. And it looks kind of like what the Gaussian function e to the minus x squared does in 1D. Okay, so this is like the 2D version of that function. And how would we compute the volume underneath this function, between this function and the x, y plane? Well, we could do it in a couple ways. We could use polar coordinates, because the function looks like it has these sort of circles in it, so that might be useful. Or we could use something like interpreting it as the union of a bunch of disk cross-sections. So that's what we're going to do. So I'm going to look at this as a bunch of disks. That are going up the z-axis. So along the z-axis, you can look at what the cross-section of our volume looks like. And you'll see that it's actually given by a disk, because right here we have this x squared plus y squared. So if z is equal to some constant c, then c equals f of xy implies, if we're just looking at a cross-section along the z-axis, then we get that f of x, c equals f of xy implies that the log of c, and here I'm just going to write log for natural log, okay? The log of c is equal to minus x squared plus y squared, which says that x squared plus y squared equals minus log c. This might look weird because it might look like I'm saying that x squared plus y squared is a negative number. But c is going to be less than 1 here, so the log of c is going to be negative. So the negative log of c is going to be positive, so it's okay. And this is exactly the equation for a circle, right? So we've shown that the cross-section of this function, this hump, with a plane on the z-axis is just going to be given by a circle. Okay, so we need to find out the area inside of the circle. And if we find out the area inside of the circle, we can integrate to add those areas up to get the volume of the full solid. Okay? And that'll give us the answer that we want. Well, what's the area inside of this circle, right? So c, remember, was equal to z. The area inside of the circle x squared plus y squared equals minus log z. Well, this is a circle of radius square root of minus log z. And the area inside that circle is just pi r squared, which is equal to minus pi log c. Okay? So now we have the area of one of our cross-sections, and we have cross-sections going from 0 all the way up to 1. Because what's the maximum value of this bump? Well, it happens when x equals y equals 0, which is e to the 0 equals 1. Okay? So that's the tallest point. And the bottom point is 0, because the exponential is positive. So we know that the integral from minus infinity to infinity, minus infinity to infinity, e to the minus x squared plus y squared, dx dy, or dy dx, is equal to the area of that bump, or the volume of that bump, which is equal to, and this just comes from multivariable calculus. It says if you do a double integral like that, then you get the volume underneath a function. But we just showed that this is equal to the area by cross sections, the volume by cross sections. So here we are integrating from z equals 0 to 1. And we wanted the area at level z, okay? But we saw that was equal to pi r squared, where r was equal to square root of minus log z. So this guy was equal to minus pi log z dc. And now we can just compute this, okay? So the pi pulls out. So does the minus sign. What is the integral of log z from 0 to 1? Okay, so we actually can compute the antiderivative of log z. So I'm going to do this for you. So what is the integral of log z dz? Well, we can use integration by parts. So integration by parts, if we stick a 1 in here, then we can integrate the 1. We can differentiate the log. We get z, what am I doing? Log z minus the integral from 0, or just the indefinite integral of, now we've got z times 1 over z, because we had to differentiate the log z part. But this guy is just equal to 1. And the integral of 1 is just equal to z. Okay? So that's the antiderivative of log. It's z log z minus z. Okay? And now we can plug this in. So we get that our integral is equal to minus pi. Now we're evaluating from 0 to 1, z log z minus z. Okay, so now we have to plug things in. When we plug in 1, we're going to get 1 times log 1. Well, log 1 is 0, minus 1, so we're going to get minus 1. And then when we plug in 0, okay, so there's something you have to check here, which is that the limit as z approaches 0 of z log z is equal to 0. Okay, so that just comes from L'Hopital or whatever you want to use to show that. So but we can also use the fact that log grows slower than any polynomial near 0. Okay, so however you want to show that, that's fine. But we end up getting 0 minus 0. Okay, and finally we get that this is equal to pi. All right, so what did we start with? We started the integral from minus infinity to infinity of e to the minus u squared du squared. And we showed that that was equal to pi. So now we just take the square root of both sides. And of course, we know the left-hand side is positive because e to the minus u squared is a positive function. So we know to take the positive square root on the right-hand side. Okay? And so we proved the Gaussian integral. And with the Gaussian integral, we have also proved that gamma of 1/2 is equal to square root of pi. Okay, so that's pretty cool. We've shown that the value of gamma of 1/2 is equal to square root of pi, which says that minus 1/2 factorial is equal to square root of pi. So now how do we use this to compute the factorial of 1/2? Well, let's use our formula to compute gamma of 3/2, which is going to be factorial of 1/2. This is equal to 1/2 times gamma of 1/2. Remember that we had gamma s plus 1 is equal to s gamma s. And we know that that's 1/2 times square root of pi. So we get square root of pi over 2 as being the factorial of 1/2. Nice. Okay, and we can go up from there. You can use this to compute the factorials of larger and larger half integers. So for example, gamma of 5/2 is equal to 3/2 times gamma of 3/2, which is just equal to 3/2 times 1/2 times square root of pi, 3/4 square root of pi, and so on and so forth. So what are you going to get for gamma of 2n plus 1 over 2, or what I should say is n plus a half. Okay, so for gamma at n plus a half, you're going to get, well, we saw that gamma at 2 plus a half, we got, so we got 2 to the n, 2 to the n on the bottom. And then on the top, we got n double factorial. Okay. So what does double factorial mean? Double factorial means that you're just going to take the odd numbers going down to 1. Okay. So in this case, I think this is fine. So in this case, if we have n equals 2, I should probably say n minus 1. There we go. Okay. So in this case, with n equals 2, we had 5 halves, and we got 2 times 2 minus 1 is 3, so we got 3 double factorial. And double factorial, I should say, equals n times n minus 2 times n minus 4, all the way down to 1, where n is an odd number. Okay. This is kind of silly notation. You'd think that double factorial would be bigger than factorial, but actually ends up being smaller. This is the product of all the odd numbers up to your number. Okay. So that's what we end up getting. And then, of course, there's a square root. So we have figured out what factorial is for the half integers. Now you might ask, okay, well, let's figure out factorials for some other fractions. And it turns out that you're going to be disappointed. So what happens is that gamma of r, for r, a rational number, is usually impossible to compute. Okay. So for example, for 1/6, 1/4, and 1/3, so the next possible sort of simple fractions that we could use, gamma of those numbers is not just irrational, but it's also algebraically independent of pi. So these numbers end up being transcendental, which means that you can't write them in terms of roots. They're not the solutions of polynomials, but they're also algebraically independent of pi, which means that you can't even write them in terms of rational numbers of pi. Like r is not going to be equal to the root of a polynomial whose coefficients involve pi and rational numbers. Okay. So that's unlike the case for r equals a half, where it was the square root of pi, which is just a root of x squared equals pi. Okay. So this is pretty nasty that you can't find the gamma function's values exactly at any of these other rational numbers. But at least we know that you can't for some of these rational numbers. Okay, so we've proven those facts. So I'm not going to prove those facts for you here because that's kind of difficult. Okay, so we have this gamma function. And so far, we've just been plugging in real numbers. What if we try to plug in s, a complex number? Well, it turns out that as long as the real part of s is greater than 0, so s comes from this part of the complex plane, then you can do it just fine. Okay? So as long as you know what it means to exponentiate by a complex number using Euler's formula, then remember Euler's formula says that e to the I theta is equal to cosine theta plus I sine theta. As long as you use that formula, you can make sense of the gamma function for complex numbers whose real part is greater than 0. Okay, but it turns out that we can make sense of the gamma function for even more complex numbers than that. So the gamma function has something called an analytic continuation. Which means that we use the properties of the gamma function to tell us what it should be at other complex numbers to C, excluding the negative integers. So remember that at the beginning of the talk, we saw that the gamma function was undefined at -1. But it turns out that the negative integers are the only negative numbers where you can't define it. you can use the gamma function at negative fractional integers. For example, we ended up finding that gamma at 1/2 was equal to square root of pi. So if we wanted to find gamma at minus 1/2, well, that would just be equal to, we know from our formula that minus 1/2 times gamma minus 1/2 is equal to gamma 1/2. But that's just equal to square root of pi. So then we just multiply that by minus 2. We get gamma minus 1/2 is equal to minus 2 square root of pi. Okay, cool. So we've shown that the gamma function can actually be defined for some negative numbers. And that's what you use in order to analytically continue it. You just use your formula for the gamma function at s minus 1 in terms of gamma function at s in order to push the gamma function all the way backwards to the negative part of the complex plane. Okay? That's what analytic continuation does here. Okay. So what is an analytic function? What does analytic continuation mean? It means that as a function from C to C, from the complex numbers themselves, it is differentiable. Okay? This is another way of understanding why the gamma function is important. Because it turns out it's really, really hard for a complex function to be differentiable, and it implies a whole lot about them. So if you're interested in these sorts of things, I really recommend you check out complex analysis. It's really beautiful. And the gamma function pops up there in various places. Okay. So what are some other properties of the gamma function that we can get from this? Well, there's something called the reflection equation for the gamma function. Okay. Which says that if you want to know what gamma is at 1 minus z, okay, then you can figure that out in terms of gamma at z. So the product of these two is actually going to be equal to something that we know very well. So this is pretty weird. Where does the sine function pop up here? Sine popped up out of nowhere. Well, this might not be too terribly surprising if you think about the fact that now we're using complex numbers. Okay, so z can be any complex number as long as it's not an integer. And in the gamma function's definition, we had an exponential. If you plug complex numbers into exponentials, you're going to end up getting sines and cosines. So this isn't too terrible, but it even holds for the real numbers. So even for the real numbers, you get this weird property. Okay. And so where does this come from? This comes from something called the Euler product formula for sine. So it turns out that you can actually write sine as a product of binomials. Okay, so an infinite product. And then if you use that infinite product, you can also find an infinite product for the gamma function and show that these work out together to conspire and give you the same thing. So I'm not going to prove that right now, but it's something you should look into if you were interested. Look into the reflection equation for the gamma function. This guy leads us to something even more crazy. So for those of you who have heard of the Riemann hypothesis, the Riemann hypothesis is about the Riemann zeta function and what its zeros are. Okay, so the Riemann zeta function is a function defined by this. Right? So if you define this infinite sum where the power at each step is s, then you can get a function which is called the Riemann zeta function. Okay, and we know the values of the Riemann zeta function at a few special values of s. So for example, zeta of 2 is going to be equal to pi squared over 6. And there are all kinds of other things that you can do. But we have never been able to figure out what the zeros of the Riemann zeta function are. Okay, so we know that there are zeros at certain places, but we can't figure out what the zeros are on this sort of critical strip, the complex numbers with real part 1/2. Okay. So this is called the Riemann hypothesis. And one piece of understanding the Riemann zeta function that you learn about when you first learn about it is called the Riemann zeta function functional equation. So how do we understand the Riemann zeta function? Sorry, my zetas are pretty messy. Okay. 1 minus s. Well, maybe we can use our gamma function property. It turns out that it has some weird formula. 2 times 2 pi to the minus s. So pi is showing up again. Cosine of pi over 2s. Gamma at s. And then zeta at s. Okay, so we've defined the zeta function in terms of, at 1 minus s in terms of the zeta function at s, and out of nowhere, gamma popped up. Okay. So the gamma function is actually an important piece of understanding the Riemann zeta function, even though it looks like from the definition, there's no factorial anywhere to be seen. Okay. And so again, this comes up from the product representation of the Riemann zeta function. So if you're interested in learning more about this, I recommend you look into these infinite products for functions. Okay. Cool. But we're not going to prove any of that today. Instead, we're going to prove something really special about the factorial. That is something that is really interesting to me, that I've used a bunch, and that I'm really excited that we're able to show a proof of it now. Okay. Because this is pretty hard to prove. So at this point, we're going to talk about something called Stirling's approximation. And it's going to get a little more tricky here. I'll give a simpler proof at first that doesn't quite get the full approximation that we want. And then I'm going to give a more complicated proof, which is going to give us the full approximation and is again going to tie the gamma function back to pi. Okay. So here we want to understand what the factorial of a large number acts like. Okay. So we can't compute it exactly. That would require multiplying a bunch of really, really big numbers. But it turns out that we can get a really good approximation for it. This approximation says that n factorial is approximately equal to the square root of 2 pi times n, so that's all under the square root, times n over e to the n. Okay, so the e here is the natural log base e. Okay, so e pops up, pi pops up. It's like a whole new Euler's formula. This is really, really weird, again, that this is a new thing that we have that's relating e and pi. And it's related to the factorial, which doesn't have an e or a pi in it at all. So it's like, where the hell did this come from? Well, first things first, I should say what I mean by twiddle. So twiddle is not just the engineer, sine x equals x approximation sort of thing. It actually has a legitimate meaning. So twiddle means n factorial over, I should say that this means n factorial over this quantity has a limit as n goes to infinity of 1. So basically it says that as n goes to infinity, these guys are getting closer and closer together. Okay. It doesn't mean that they're actually getting closer and closer in terms of like they're converging to each other. Okay. If that were happening, that would be even better. But it does mean that relative to their sizes, they're getting closer and closer together. What's an example of this? Like e to the x plus c is twiddle e to the x. Right? Because e to the x over e to the x plus c over e to the x as x goes to infinity is just equal to 1. Okay? But 2e to the x is not twiddle e to the x because 2e to the x over e to the x goes to 2. Right? So twiddle is basically saying you're asymptotically equivalent in the long run. So we understand now what twiddle means. So let's try to understand Stirling's approximation. Well, first of all, what is this formula on the right-hand side? The main part of the formula comes from the n to the n over e to the n part, if you distribute that exponent. Okay. So factorial is going to grow kind of like n to the n, which is a really, really fast-growing function. But we also have this extra factor of square root of n, and then we have a constant, square root of 2 pi. Okay? So it says it grows just a little bit faster than n over e to the n. Okay. And this is useful for computing large values of gamma or large values of factorial, because we can take powers of numbers more easily than we can take factorials of numbers. So let's try to prove this. First things first, we're going to prove a weaker form, okay? We're going to get the Stirling approximation, but without the square root of 2 pi. We're just going to get an arbitrary constant. So this is called like a big theta asymptotic, where we know now that it grows like this function, but we don't know what the actual constant is when you divide them. Okay. So how do we do something like that? Oops. So we have n factorial, and we want to understand it. So the first thing that we could do is we could take the log of it. And when we take the log, we're going to kill a lot of information. In particular, as n goes to infinity, we'll kill things like multiplicative constants. So this is kind of expected that we're going to kill that square root of 2 pi. Well, what is the log of n factorial? It's the log of n times n minus 1 times n minus 2, etc. But we know from log rules that we can split this into a sum of logs. So this is the sum from, I'm going to say k equals 1 to n, of log of k. Right? So I've just broken the product into a sum of logs. And then this guy right here is nearly equal to the integral of log from 1 to n. Okay, that's sort of a tricky statement to say. How do I want to, justify that? So let's look at the integral. So this is the log function. And the sum we're looking at would be to basically say, okay, we have a piece here. 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 And so on and so forth. Okay? So the sum is giving us all those rectangles. So this is kind of like a Riemann sum for log. Okay, but a Riemann sum for log isn't exactly what we want in order to get a good approximation. What if instead we use a trapezoidal sum? So a trapezoidal sum, remember, is like this. Oops. Where you draw a line between each, and then you draw the trapezoids to approximate the integral. And this is going to turn out to be a really, really good approximation for the integral. It's good enough to get us this twiddle, okay? So what is the trapezoidal approximation? Well, at each trapezoid, we're going to have the value log of k minus 1 plus, which is the left side, and the right side will be the value of log k. Okay. The width is just 1, and we know the area of a trapezoid with sides, or with bases a and b, and width h is h times the average of a and b. Okay. So we're just going to get this over 2 times 1. Just the height. Okay? So we get this for each of the trapezoids, and now we're going to add those up. So we'll have log of 1 plus log of 2 over 2 plus log of 2 plus log of 3 over 2 plus so on plus log of n minus 1 plus log of n over 2. But now we can notice that this guy right here pairs up with that guy right there. So we can actually reorganize all of the sums. So first of all, I'm going to pull out a factor of 2 because they all have a 2 in them. And then I'm going to push the paired terms together. So I'm going to get 1/2 log of 1 plus 2 log 2 plus 2 log 3 plus 2 log 4, all the way up to 2 log n minus 1, plus, and now it's just log n. I don't have a pair for log n. Okay, so that's good. And now what I can do is I can divide by 2. So here I'm going to remember the fact that, So I'm going to pull forth an extra log 1 and an extra log n, and then divide by 2. So I'm going to say that if I add and subtract log 1 and log n, or over 2, then I'm going to get that this is equal to the sum of log n, right? Because I added in, I should say log k. If I add in extra log 1 and log n, but then I have to subtract those. And then they each get in half. Okay? So this is what I get as my approximation to the integral from 1 to n of log n. Log x. Okay. So it turns out that this is twiddle. I didn't prove it, but if you divide these, then you're going to get something that limits to 1 as n goes to infinity. In fact, it's even better than twiddle. If you subtract these, you're going to get something that limits to a constant as n goes to infinity. So the difference between the sum of log and the integral of log goes to a constant as n goes to infinity. This is related to something called the Euler-Mascheroni constant. This is something that you can look into if you're interested in. It's related to the difference between log of n and the harmonic series, 1 plus 1/2 plus 1/3, etc. up to 1 over n. That minus log n as n goes to infinity converges to a number called the Euler-Mascheroni constant, and then you can use that to understand that these two are never more than a constant number apart. Okay, so because of that, if we take e to both of these, so if the difference between this thing, I'm going to call this g of n, and I'm going to call this f of n, right? So if g of n minus f of n is always less than or equal to a constant, right? So I'm going to, whatever, it doesn't matter. I'm going to say if it's about equal to a constant for large n, then if I take e to both sides, then they're going to be separated by a constant. So now I'm going to say that what I should say is that this guy is converging to a constant as n goes to infinity. And so then if I take e to both sides, that converges to a constant. And so then now I can multiply both sides by f of n, and I get that g of e to the gn is twiddle e to the c, e to the f of n. Okay. So again, the better way to do this is to divide by c to pull out the f of n. You get that e to the gn over e to the f of n. E to the c is going to 1. So then you know that e to the gn is twiddle e to the c, e to the fn. Okay, why am I dealing with e's here? So that I can take the exponent of both sides. So I take the exponent of both sides, and I get the sum of log k minus 1/2 log 1 minus 1/2 log n. Oh, here I should use the fact that log 1 is just equal to 0, so I can get rid of that. And then I have minus 1/2 log 1. So e to the sum of k equals 1 to n log n minus 1/2 log 1, or log n, is twiddle the e to the integral from 1 to n log x dx, e to the c. Okay, c is just a constant. We don't know what the constant is. Okay, and then now I can use what we did. So we know that e to the log n, or e to the sum of log n, is just e to the log n factorial. So we already showed that the sum of log n is just, this should be okay. the sum of log k is just equal to log n factorial. And then the other part here is e to the 1/2 log n. So I'm going to use a log rule to push the 1/2 inside. And then e to the log n 1/2 is just n to the 1/2. I also have a minus sign. So the minus sign is going to make this, that's going to go in there. It's going to make this n to the minus 1/2. Okay. So e to the log n factorial. And then I'm going to use e to the log n factorial as n factorial. So n factorial n to the minus 1/2 is twiddle e to the c. Okay, now on this side I need to do an integral. So remember that we computed the antiderivative of log. So we know that this is n log n minus n. And then minus the value at 1. So that was x log, or 1 log 1 minus 1. So that gives me a plus 1. Okay. And now we've got this extra thing. So now we need to work it out. So e to the n log n minus n plus 1. Okay. So I'm going to use log rules to push the n in here. I'm going to put the plus 1 with c. So this guy is now c plus 1. And then I'm going to use log rules again to say that this is e to the log n to the n, e to the minus n. And then finally I'm going to say this is e to the c plus 1. E to the log n and n is just n to the n. And then e to the minus n, which is just equal to 1 over e to the n, which is equal to n over e to the n. Great, okay. And now we'll multiply both sides by n to the minus 1/2. We'll get the n factorial is twiddle. This guy here is just a new constant, e to the c plus 1. I'm going to call that d. It's twiddle d square root of n, because n to the 1/2, n over e to the n. Okay, and we got Stirling's approximation, but without the square root of 2 pi. So now we need to show that d is equal to square root of 2 pi. Yeah. So that's pretty cool so far. How do we show something like e is equal to the square root of 2 pi, or d is equal to the square root of 2 pi? Well, it turns out that the technique that we used is not powerful enough. We need to go to something totally different. Okay? So the first thing that I'm going to do is I'm going to rewrite the gamma function. So the gamma function is going to come back into the picture now. We're going to do something with the gamma function in order to figure out what that constant is. The gamma function will come back into the picture, and I'm going to apply something to it called the method of steepest descent. It's also known as Laplace's method. So let's write down what the gamma function is again. Remember that we're interested in n factorial, which was equal to gamma at s plus 1, or n plus 1. So let's write this down this way. Okay. So now I'm going to write down the integral. The integral is just equal to the integral from 0 to infinity, t to the s, e to the minus t dt. Because we evaluated s plus 1, we just get t to the s. Okay, and now I'm going to do a clever u substitution. I'm going to write t is equal to s times x. Okay, so s is our variable, but I'm just scaling t by that variable. So now dt is equal to s dx. All right, and if we substitute this in, then we're going to get the integral from 0 to infinity. T is s of x, so we get s x to the s, e to the minus s x, and then s dx. Okay, so we can pull out the s's because this integral is in terms of x. So s to the s times s is just s to the s plus 1. X to the s, e to the minus sx dx. Oh, and I should have mentioned that the integral, as long as s is greater than 0, then the bounds of integration don't change. If you have t being 0, then you get x equals 0. If you have t is infinity, x is infinity. Okay. All right. And so now we have this integral right here. What I'm going to do is I'm going to write x to the s is equal to e to the log, so s log of x. And why am I going to do that? So that I can combine the two exponents. So I get s to the s plus 1, the integral from 0 to infinity of, now I combine these two exponents, e to the s times log x minus x. So this is a weird way of writing the gamma function, but it's a way of writing the gamma function. In particular, if I write gamma at s plus 1 over s to the s plus 1, I know that this is equal to the integral from 0 to infinity of e to the s times this weird function. Okay. So how do I understand what the integral of this is? Well, I definitely can't take the integral directly, but what I can do is I can understand what happens as s gets big. Okay. So how do I do something like that? Well, this comes from something called Laplace's method, or something called the method of steepest descent. So what's the picture here? The function log of x minus x looks something like this. So draw further down. So for x big, the log part is not that big, and the minus x part dominates. So for x big, we get something that's going like that. For x small, the x part is near 0, and log x is very negative. So we get something like that. So we have some function like this, and then in particular at x equals 1, we have log of 1 equals 0, and we get minus 1. So this at x equals 1, we get minus 1. And this is actually going to turn out to be the max of the function. Okay. So if we take e to this function, we're going to get some new function, all right? But now what happens if we make this number s really big? So if we multiply this function by a very, very big number s, e to some big number is going to be really big, but e to some big negative number, because log x minus x is negative, e to some big negative number is going to be really, really, really small. Okay. So if s gets bigger and bigger, this log x minus x part gets more and more negative, and so then we get a smaller and smaller number, e to the s log x minus x. So you'd expect that this integral will be really, really small. But more importantly, log x minus x is not always the same smallness. So sometimes it's really, really negative, and sometimes it's not that negative. So for example, at x equals 1, the function's not that negative, it's just minus 1. And so we get e to the s times minus 1, which e to the minus s is decaying, but is not decaying as quickly as, for example, when you're like here, where you get e to the s times minus 4, say, and then you get e to the minus 4s. And as s grows, that goes to 0 a lot quicker than this goes to 0. And even more so for other points. Okay. So pretty much anywhere where you're not at that max, you're going to be decaying quicker than you are when you're at the max, because e to the s times a negative number is going to get larger and larger the bigger that we make s. Or sorry, it's going to get smaller and smaller more and more quickly the bigger that we make s. Okay. So this is where the idea comes from. It comes from this idea that if you take e to a large negative number, then we get something very, very small. Okay? And so this tells us that maybe we just care about what's going on near the maximum. Okay? And so that's what the method of steepest descent tells us. Okay. So I'm going to write down what the method of steepest descent is, and then we're going to draw a picture, and then we're going to go ahead and prove it, and we'll use it to show that the gamma function, we'll use it to show the Stirling approximation. So the method of steepest descent is going to put into math what I just said in words. So if we have f, some smooth function, with a global max at some c in an interval ab, and at that global max, the second derivative is negative. Okay, so this is what you expect for a local max, that the second derivative is decreasing there. Okay. Or is not decreasing, but that the function is concave down, that the first derivative is decreasing. Then the integral from a to b of e to the s f of x dx. So the x here is the variable of integration. S is the number that we're going to be making bigger. It is twiddle square root of 2 pi times 1 over the square root of minus f double prime at c times 1 over square root of s times e to the s f of c. Okay, what the hell is this? This is such a weird formula that I've just written down. It has a bunch of square roots in it. Where did any of this come from? This is something called an integral asymptotic. So it says that as you make s bigger and bigger and bigger, then this integral is getting closer and closer to this weird formula. Okay, but it's a weird formula, but it's a formula that we can compute exactly. We know what the value of this formula is, right? Because we know what f of c is. That's just c was the global max. We can compute that using, f prime equals 0. We can compute f double prime at c. We know what s is. So this is something that we can actually compute. We can compute this value for how the integral should be acting for large s. Okay, where does this come from anyway? Well, the first thing that we could do is we could try to make f into something a little bit simpler to understand. So we see this e to the s f of c over here. So what if I divide both sides by e to the s f of c? So under the integral, because e to the s f of c is just a constant, I'm just going to get f of x minus f of c dx. So what I did was I multiplied both sides by e to the minus f of c, e to the minus s f of c. And then under the integral, I just combine those to get e to the s f of x minus f of c. Let's write all these things together. So square root of 2 pi over minus s f double prime c. That's fine. Okay. All right. So what I did here was I just made it so that our function, which I'm going to call this new function g of x equals f of x minus f of c. So I made it so that now the function has a global max of 0. So f of x was some function like this, maybe. And then I've just defined a new function g of x. This is not what I want. Hang on. F of x is some function like this. G of x is some function where I've just shifted it, so now the global max is at 0. Okay. Okay, and right now I'm just doing this to help us understand this formula, right? I'm just trying to get rid of the stuff that's kind of irrelevant, do some shifts to understand what the formula says. Okay. And then, of course, g double prime is just equal to f double prime, because f of c is just a constant. So I can replace things in my integral. Okay. And then the other thing that I can do is I can shift the c to 0. So what I'm going to do is I'm going to use a shift x moving to x plus c. Okay. And if I do that, I'm going to get a new function h of x, which is equal to g of x minus c. So that now the max of h happens at, right. So now at h equals 0, you're going to get g of, this isn't what I want. What I want is x plus c. Okay, there. When I do h of 0, you're going to get g of c, which is just equal to the max. Okay, so I'm just shifting things so that now the max is at 0, 0. Okay. And when I put in h of x equals g of x plus c, well, g double prime at c is going to become h double prime at 0, and the integral is not going to change. All that's going to change are the bounds of integration. So now a is going to be, well, a used to be where x started, so now it's going to be a minus c. I think that should be right. It may be a plus c, a b plus c, but it doesn't matter. I'm just going to change these to a prime and b prime because we've got new bounds of integration. The point is that I've basically reduced our formula to understanding a function h, which has a global max at 0, 0. Okay? Why is this a useful way to reduce the formula? Well, if you take e to such a function, what do you get? Okay, at 0, you're going to go up to 1, because e to the 0 equals 1. And then as it gets negative, it's going to decay quickly. Right, so for more and more negative h, then e to the hx is going to be smaller and smaller. Okay? Now what happens when I put in an s? So the s is getting bigger and bigger, and at x equals 0, this is just always going to be equal to 0. H of 0 equals 0, so we're going to get 1 for all time, or for all s. But for all the other possible values of s, so like for x equals 1, for x equals minus 1, and so on, we're going to get a negative value for h, and as s grows, that's going to get really, really negative. Okay? And so then e to that is going to get really, really small. So for all the other values, as s grows, this is going to shrink, shrink, shrink down. Okay? But at 0, it'll always stay at 1. Okay. And so you can see that the integral is shrinking to 0 here, and that only the value at h of 0 mattered. All right? So only the behavior around h of 0 mattered. So this is where this is coming from. We understand the integral in terms of its behavior at 0. And then we have to understand what the size of that bump is, right? Because we're trying to find the integral, so the integral is just going to be the size of this bump. And it's going to turn out that the size of that bump is going to be proportional to square root of 2 pi over minus s, or over s. Okay. So how do we prove something like this? Let's prove the method of steepest descent. So we're going to stick with our function h of x, which we had defined just by shifting our f so that the maximum happened at x equals 0 and was equal to x equals 0. Okay. So this is our function h. And by Taylor's theorem, we know that this guy is basically like a parabola at x equals 0. Okay? In fact, because h double prime was strictly negative, by continuity, we can find, so let's pick an epsilon and find delta greater than 0. So we're finding a delta so that as long as x is less than delta, then f double prime at x is going to be greater than or equal to f double prime at 0 minus epsilon. So the point here is that I'm just making sure that, and then I also want it to be above. Okay. So I'm making sure that the second derivative is within epsilon of the second derivative at 0. Okay, so this is just coming from the definition of continuity. For small enough x, f double prime at 0 is close to f double prime at x. Okay, and then using Taylor's theorem, I can say that that implies that f at x, so here I'm basically integrating twice, f of x is between two values. It's between f double prime at 0 minus epsilon over 2 times x squared, and then f double prime, I should say plus, f double prime at 0 minus epsilon over 2 times x squared. Okay. So where does that come from? Taylor's theorem says that f of x is equal to f of 0 plus, oh my god, I'm using f here. I should be using h. This is h. Sorry. Okay, so that's h. So Taylor's theorem says that h at h of x is equal to h of 0 plus h prime of 0 times x plus h double prime of 0 over 2 times x squared plus some error for small x. And h of 0 is equal to 0 because I shifted it down so that the max is at 0. And h prime of 0 is equal to 0 because 0 is a global max, and h prime at a max is 0. Okay. So we just end up with h of x is equal to h double prime of 0 over 2 times x squared. Okay. In particular, if I add a little bit to that parabola and I subtract a little bit from that parabola, so this guy is h prime 0 plus x over 2, h prime 0 plus epsilon over 2 times x squared. This guy is h double prime 0 minus epsilon over 2 times x squared. Then I get something that sandwiches my function between two parabolas. Okay? At least for small enough x. So this is for x less than delta. So I've sandwiched my function between two parabolas like this. Okay? And now what I'm going to do is I'm going to use the value of the integrals on the parabolas to bound the value of the integral of the function. Okay? So what did we want to understand? We wanted to understand the integral from a to b of e to the s f of x, or e to the s h of x dx. Okay, well I can bound that above and below. So let's do the below bound first. It's a little easier. So because the exponential is positive, if I cut out parts of the integral, then I'm just going to get something smaller, right? So if you have a positive function, you integrate over a smaller interval, you get a smaller integral. So I'm going to cut out the part of the integral that's not near delta. So I'm just going to be integrating from minus delta to delta now. And then I'm going to replace, first I'll write e to the s hx dx, right? But then I can replace hx by the lower bound, right? So I can say that this is greater than, and so that is greater than the thing where I replace h of x by the lower bound, by the thing that's smaller than it. Because I know that for x less than delta, this guy is smaller than this. So if I replace this, I get h double prime 0 minus epsilon over 2 x squared. Okay, and dx. All right. So now what I can do is I can do a u substitution. So let's say that u is equal to the square root. Oh, and I can't forget that I have e to the s times that. Okay. So I'm going to do a u substitution with u is equal to s times, let's see, epsilon minus f double, or h double prime to 0. Okay, I'm going to throw in a 2, over 2. Put that under the square root times x. Okay, why am I doing this u substitution? I'm doing this u substitution so that when I plug in, like when I square this, I get that x squared is equal to u squared times the thing, or when I square this, I get that u squared is equal to x squared times s epsilon minus h double prime 0 over 2, so that when I multiply, or when I substitute this in, I'm going to get minus u squared. So yeah, that's what I'm going to do. So this guy. Okay, and then what are the integral bounds end up being? Well, I'm going to call this thing like k or something like that. And then I'm going to get minus k delta to k delta. I'm going to get e to the minus u squared du. Okay, but then what's du? It's equal to this thing dx. So now I need to multiply by 1 over k. So that's what the integral ends up being equal to. Okay, but now what I can do is I can use the fact that s is going to infinity. So as s goes to infinity, k goes to infinity, right? And this thing is just equal to, as s goes to infinity, well, k goes to infinity here, k goes to infinity there. So the integral goes to infinity. And I should really write a twiddle. It'll end up being fine. Okay, e to the minus u squared du times 1 over k. Okay. This guy is just equal to square root of pi. We already showed that. And so you're going to get square root of pi over k. So this is for large S. We get that the lower bound what should I say here? I should say that square root of pi over k is lower bound, so it's not quite twiddle yet, but it's at least a beneath twiddle for e to the s hx dx. Okay. What about the upper bound? So we do something similar for that. So the integral from a to b e to the s hx dx. Okay, for the upper bound, we can't quite get rid of the a and b and just replace with minus delta and delta like we did before. If we do that, then we're going to be dropping stuff, and we're trying to get something bigger, so we can't do that. But it turns out that those terms are going to be easy to deal with. So let's split it up into 3 parts. Okay, the middle part is going to be handled very, very similarly to before, right? So what I've done here is I've split the integral up into the integral from a to minus delta, the integral from minus delta to delta, and the integral from delta to b. The middle part is going to be handled really, really similar to what we did before, except now we're going to end up with a new constant. So I'm going to call this constant L, which is equal to the square root of minus epsilon minus h double prime 0 times s over 2, and make the square root big enough. Okay, and then what we're going to do is we're going to end up with the integral from minus delta L to delta L. So I'm going to say this is less than or equal to, where what I've done here is I've just used my upper bound to replace with x squared. This is integral from minus delta L to delta L of e to the minus e squared du times 1 over L. So I'm doing the same thing I did before. And then I can say that this is twiddle above square root of pi over L. All right. Okay, so that's fine. And now we need to deal with the extra terms. So let's deal with the lower one. And the upper one's going to be exactly the same. So we want to show that these things go to 0. These don't matter. And this is going to make sense because when x is bigger than delta, h of x is going to be smaller than the max, right? So when x was near delta, then h of x was near the max. But because this is a global max, this says that h of x is going to be less than h of 0 minus some constant, which depends on delta, right? So, delta will be, let me draw a picture. If you pick your delta to be this, okay, so we're looking at only at x's which are in this range. Then if you look outside of that box, so this is x less than delta. If you look outside of that box, then your function h is going to be smaller, right? So it's going to be smaller at least by that. So h at x, for x outside of delta, is going to be smaller than h of 0 minus c of delta, for some c of delta that's positive. Because we had a max. Okay. The point being that you don't come back to the max later on, because it's global. All right. So what does that mean? That means that that we can write this down as the integral from a to delta minus delta e to the shx dx. And then we can use that hx is less than h0 minus c delta. We know that h0 is just 0, so this is less than e to the minus s c delta. And then as s goes to infinity, well, okay, we can just integrate this directly. So this is equal to how do you integrate this? Oh, I mean, it's just a constant. It'll be minus delta minus a times e to the minus s c delta. And then as s goes to infinity, this goes to 0. Okay, so that's fine. All right, and the upper bound is very, very similar. You're going to bound by b minus delta times e to the minus sc delta, and then as s goes to infinity, you're going to get 0. Okay, so these outer terms don't matter. And this comes from the fact that, like here, so this was the delta region when we did e to the s hx, and then outside, we go to 0 really, really quickly. Okay. All right. So with all of this, what we have shown is that square root of pi over k is less than or equal to, or at least twiddle less than or equal to the thing we wanted to understand, which is twiddle less than or equal to something which is going to 0, plus square root of pi over L. Okay, so now we need to understand why this is okay. So what is k? K was equal to, so what is square root of pi over k, I should say. So square root of pi over k is square root of pi times square root of 2 over square root of s times epsilon minus h double prime 0. Okay, which is square root of 2 pi over, let's write it all together, that, and then square root of pi over L was square root of 2 pi over, now we have s, and we have minus epsilon minus h double prime at 0. Okay, so now we have these two things, which are going to give us something that we want as epsilon goes to 0. So now we picked epsilon arbitrary, so now let epsilon go to 0. The epsilon is going to go away. And we'll get that the integral from a to b, e to the s hx dx, is equal to the square root, or not equal, but it's twiddle at least, the square root of 2 pi over s times minus h double prime is 0. Great. Okay, so we did it. We finally proved Stirling's formula. Or not Stirling's formula, we finally proved the method of steepest descent. Okay, so remember that that if you are going to use this for a function which doesn't have its max at 0 and doesn't have the max centered, then this guy will turn into where the max is, and then we'll also get a factor of e to the s times the location, or the value of the max, okay? And remember, again, we just got rid of those things by shifting the function and by shrinking the max to 0, okay? So this is the proof of method of steepest descent. I was a little bit shaky with some things. If you want a more clear proof, you can look at the page for method of steepest descent or Laplace's method on Wikipedia. It gives a very, very detailed proof, which takes a lot longer to do. Okay. So now how do we use this to finally get Stirling's formula? Well, remember that we had at the beginning that gamma at s plus 1 over s, the s plus 1, was equal to the integral from 0 to infinity of e to the s log x minus x dx. Okay. Oh, the problem here is that we have integral bounds from 0 to infinity, and here our integral bounds are finite. This isn't much of an issue. You can just make the integral bounds finite and then show that outside you get something really, really small that gets smaller and smaller as s goes to infinity. It's just like how we had here, how the further away that you get from the origin, as long as your function is decaying, the further away you get from the origin, the smaller it gets. This doesn't really matter. It's fine. Okay. So the integral bound from 0 to infinity is fine. And what we want to do is we want to use f of x, or h of x in this case. H of x is equal to log of x minus x. Okay, we need to figure out where the max is, and we need to figure out what f double prime at the max, or h double prime at the max is. Okay, so h prime of x is equal to 1 over x minus 1. So this is equal to 0 when x equals 1. So the max occurs at x equals 1. And then we need to figure out what h double prime at 1 is. So h double prime of x is equal to minus 1 over x squared. So h double prime at 1 is just equal to minus 1. Okay. And so now we have everything that we need in order to apply the method of steepest descent. So we get that the integral from 0 to infinity of e to the s log x minus x dx is equal to, or is twiddle? Well, what does method of steepest descent tell us? It tells us this is twiddle square root of 2 pi over s times minus h double prime at the max, which is minus 1, which is 1, times e to the s times whatever the value of h is at the max, so h of 1. H of 1 is just 1 minus 0, 0 minus 1. So this gives us minus 1. Okay, and we got it. We got that gamma at s over s, the s plus 1, is twiddle square root of 2 pi times 1 over squared s times e to the minus s. Okay, now we multiply by s to the s plus 1, and we get that gamma s, this was gamma s plus 1, this was gamma s plus 1, good. Okay, that's gamma s plus 1. Gamma s plus 1 is twiddle square root of 2 pi. Now I'm going to steal the s plus 1, I'm going to steal the s from s plus 1, so I'm going to get s to the s times 1 over square root of s times e to the minus s. The s to the s and the e to the minus s I'm going to combine, and the s and this 1 over square root of s I'm going to combine. This is equal to square root of 2 pi times square root of s times s over e to the s. And we did it. We proved Stirling's formula. Okay, so this is kind of a crazy proof. It turns out that this is one of the easiest ways to prove Stirling's formula and find that constant. You can also use the Bernoulli numbers if you know what those are. There are various other ways to do it, but using the method of steepest descent is a really neat way to do it. Okay. Now, the method of steepest descent, I'll say a few more words about it, is really, really closely related to something that's even more important in math called the method of stationary phase. So what's the method of stationary phase? This is when we take this e to the s hx that we want to understand, and instead we want to understand e to the I s hx. So now we have a complex exponential, and that means that our exponential, or our exponent is spinning. Okay, so we're not our exponent, but our function is spinning. And so what the method of stationary phase tells you is that when you're spinning really, really fast, things cancel out and you end up not counting that stuff. And when you spin slowly, so when your first derivative is 0, for example, when you have a max, then you are not going to cancel things out and you'll get contributions for those points. Okay? So the method of stationary phase is very, very similar to the method of steepest descent. Method of steepest descent is about how you kind of fall off really quickly. And the method of stationary phase is about when you stop rotating. Okay, so these are kind of similar ideas. Method of stationary phase comes up a lot if you're studying like quantum mechanics or things like that, and various other kinds of mathematical physics. So it's a really, really important idea. But for this talk, all we needed was the method of steepest descent. Okay. So thank you very much for listening. If you have any questions, feel free to ask. You can ping me in the Math Discord with further questions. I'll put some links in the video description with places where you can go to look at proper proofs of these things. In particular, I mentioned the Bohr-Mellerup theorem. I mentioned the Riemann zeta functional equation. And I mentioned, well, we talked about the proof of the method of steepest descent, but I'll give you a more complete proof if you want to see that. And thank you very much for watching. Bye.